Hello, it's Desmond Parker with A Plus College Ready. Today we are going to talk about molecular geometry and valence shell electron pair repulsion theory. Now, we call that, instead of saying valence shell electron pair repulsion theory, we say Vesper theory. And it's not as hard as it sounds, so don't get overwhelmed by the name. You know, chemists, we love to have fancy names for everything, and this is just one of those things. So, molecule polarity, I've talked to you guys several times that polarity really determines whether or not a molecule is. I'm sorry, that we said that molecular geometry determines whether or not a molecule is polar. So, if a molecule has a geometry which is bent, or anything but linear, or tetrahedral, or trigonal planar, or octahedral, and there might be one I'm missing, um, it will become polar. So other than those, it's polar. And the peripheral atoms have to be the same all the way around. So if I have, like in this example here, for instance, if one of those oxygens was exchanged for a sulfur, which I don't think would actually happen, then the molecule would no longer be symmetrical, so therefore it would be polar. And that's because our what we call our dipole forces, they are vector quantities. And since they are vectors, when the molecule isn't linear or tetrahedral or it has the ability to cancel out, it will be polar. So with Vesper theory, we only use the central atom or whatever atom we decide to focus in on. For our larger molecules, such as those hydrocarbons, or those organic molecules, usually they will specify to you if they want to know some information about shape of the molecule or something along those lines. They will specify which one they're talking about. So with Vesper, in general, we only use the central atom to determine the geometry. Bonded atoms and lone pairs are the only thing that we focus on, and we call those areas of electron density, or they call them electron domains commonly. So lone pairs, each pair counts as one area of electron density or one domain. Each bond, regardless to whether or not it's a single, double, or triple, counts as one area of electron density, one electron domain. So when we add a lone pair to the top of our atom, it causes those bonding domains to be pushed a little bit further down, which causes the geometry to change. So we have two types of bonds. We have sigma bonds and we have pi bonds. With our single bonds, they're made up of only one sigma, and sigma bonds tend to be stronger than pi bonds are, which we talked about that in the very first video. Our double bonds consist of one sigma bond and one pi bond, and our triple bonds consist of one sigma bond and two pi bonds. So that's why a triple bond is not necessarily 3 times stronger than a single bond, because again, like I told you a minute ago, pi bonds are not strong bonds, are not as strong as sigma bonds. So it's not necessarily like it would translate to be 3 times stronger than a sigma. So it's only slightly stronger than, relatively stronger, but not triply stronger. So the way that these bonds orient themselves is a head-to-tail orientation, which again, that's not really all that important, but that's just some information that you might want to know. And we have what's called hybridization, and we have degenerate orbital hybridization, which are energy orbitals that are at the same energy level, which will then hybridize to form are different types of bonds. So we can really count the bonds to determine how much or what the hybridization of that is. So if we have one bond, then we have one s orbital that's being used. If we have two bonds, then we have one s orbital and we will have one p orbital, which will be used. And then three bonds, one s orbital, and two p orbitals being used, and so on and so forth. So that's how we can designate the type of hybridization that's occurring in that molecule by looking at. And I should say further that it's not simply just the bonds, it's really the bonds and the lone pairs of electrons which determine the hybridization of the molecule. So it's not simply just a bond. So when these atoms hybridize, they will then occupy a portion of their orbital and the portion of the orbital of the other atom during that hybridization process, which is what allows us to determine that. So these pi bonds have a side-by-side orientation versus the sigma bonds, which have a head-to-tail orientation. So again, that's not necessary for you to really know for your AP exam. They ask you maybe one or two questions about sigma and pi bonding. So let's get into molecular geometry. That's why we're here today. So planar molecules are arranged in one plane of our system. So remember, these molecules are three-dimensional, but all of those molecules lie in a single plane. So such planar molecules are linear, and they have a separation of 180 degrees from each other. Its hybridization is sp because it has two bonds, or two areas of electron density, or two domains. Trigonal-planar, which again is in a plane, so it has a hybridization of sp2 because it has three areas of electron density, so it has one s and two p's, and its bond angle is going to be 120 degrees. A bent molecule has a hybridization which should be sp2 because it has two bonds and one area that is a lone pair of electrons, which gives it three areas of electron density. And that bond angle is going to be approximately 1/16. You have to know bond angles. Bond angles will be asked. If you know the general bond angle, then it really does help you get the others. So it's typically one lone pair will push 2 degrees. 2 to 4 degrees. It all depends. So there's a range that they do accept, but I believe it's 2 to 4 degrees that it will push them down. I got to redo this video. So again, 3 dimensions. So our shapes will occur in 3 dimensions. One that we have is a bent. So this right here, what I like to call a bent tetrahedral, because you have a bent trigonal planar and you also have a bent tetrahedral molecule. So there are two types of bent molecules. Water is one of the most common ones, and since there are 4 areas of electron density, it has a hybridization of sp3 with bond angles of approximately 105 degrees. Tetrahedral molecules, which have one central atom and 4 atoms attached to it, have a hybridization of sp3 because there are 4 areas of electron density, and its bond angle is about 105 degrees, 109.5 degrees. Trigonal-Pyramidal, this is from the tetrahedral family. So its hybridization did not change. And since it has that lone pair, it pushed the bond angle down to about 170 degrees. Again, there is a range of numbers that they will take for your bond angle within reason. Now, they're not going to take something that's like 120 degrees for this right here, but they'll take, I think, on one of the tests, they took between like 106 and 108 degrees. So they just want you to know that the bond angle is going to get shorter. By exactly how much, again, that can be debatable at times. But since we have 4 areas of electron density, remember hybridization is sp3. Trigonal Bi-pyramidal. This molecule right here has a hybridization of sp3d. So remember, we only have 3 p orbitals that are available for use. So once they're all filled up, then we're going to go ahead and have to go into the d orbital. So this has to be an atom which has a d orbital available. If you don't have a d orbital available, then you will not form a trigonal bipyramidal molecule. And it has 2 bond angles of 120 and 90 degrees. So anything past tetrahedral, for the purposes of AP, you do not need to have memorized. However, it depends on what your teacher requires of you, which will really depend upon which one of these you actually need to know. But you need to know all the geometries up to tetrahedral, bond angles, and hybridization. And lastly, we have Octahedral, which has a hybridization of sp3d2. Again, molecules with d orbitals can have an octahedral geometry. If it does not have a d orbital available, it will not form this geometry at all. So let's take a look at a question about hybridization. So it says, when reaction 3 occurs, does the hybridization of the carbon atoms change? So go ahead and pause the video. Alright, so let's look at this molecule. So we have carbon, hydrogen, hydrogen. You guys got to be able to draw these molecules out. So we have 2 areas of electron density. So these carbons are both considered to be sp. And then if we were to draw this other molecule right here out, we will have carbon, carbon, and it really doesn't matter where you put these guys right here, because we're only really concerned about the central atom. So we don't really know where these are located, but it could look something like this. So now we want to look at this carbon molecule, and we'll see that there are 3 areas of electron density. So that means that this is sp2. So it should be A for the answer. Let's see what it actually is. Yes, it's A. So there are going to be hybridization questions on there. The BF3 molecule is nonpolar, where NF3 molecule is polar. Which of the following statements about the difference in polarity of the 2 molecules? So before, go ahead and pause the video and then we'll talk about it. Alright, so before I even look at this, it told me BF3 molecule is nonpolar. So me knowing that it's nonpolar, I should hopefully be able to recognize that this has symmetry. Whereas, since this one's nonpolar, this is asymmetrical. So you should be able to immediately recognize that. So then we can look at which answer choices don't make sense. So in NF3, each F joined to the end with multiple bonds. So we should know that that's not true, because nitrogen, although it can form double bonds, fluorine cannot. So we can eliminate this one right here based off letter A, based off of it talking about nitrogen forming double bonds. Nitrogen fluorine bonds are polar where boron fluorine bonds are nonpolar. B is not true. This right here has polar bonds. These are polar. But again, we talked earlier and I told you that a molecule can have polar bonds but still be nonpolar if it is a symmetrical compound. So we know that B should not be one of our answer choices. C, NF3 is ionic. That should be immediate giveaway that that's incorrect. And then it says, unlike BF3, NF3 has a non-planar geometry due to an unshared pair. So this unshared pair, and I did not mean to do that. So this unshared pair that this is talking about forces this molecule to be asymmetrical. So it pushes those peripheral atoms down by about 2 degrees or so. So we should see that D should be our answer. And it is. So this is question 35. This is, I would still consider this to be about the middle of the test. So this one would be considered a harder question. And if you got that one, you're doing good. And then 27, which represents the molecule that contains the smallest bond angle. So go ahead, pause the video, and we will go back to this. All right. Now, A, B, C, and D. I would hope that we could immediately eliminate C, because without those lone pair of electrons on C, it is going to have a trigonal planar geometry, which means its maximum separation will be about 120. We could eliminate A as well, because again, this is a tetrahedral. Tetrahedral geometries have a bond angle of about 109.5 degrees. So that leaves us with boron and, with B and D. So B is a derivative of A, and D is a derivative of C. Ish. So if I remove a bonding pair of electrons off of C, I get D, which means that that's going to push that bond angle down, decrease it by about 2 to 4 degrees. So we said earlier that this is 120. So then this one would have to be about between 118 and 116. For A, we said it's 109 degrees. Which means that it's going to push this down by about 2 degrees, 2 to 4 degrees. So it's going to be between 107 or 106 and 107, something like that. But anyway, B should be our answer for this, because it should have the smallest bond angle, and it does. Alright, so I hope that this video was helpful. If you have any questions, again, make sure that you forward them to your instructor, and I will see you guys for our last video, which deals with intermolecular forces.